AC analysis on coupled circuits. So today we will see AC analysis in the topic of coupled circuits. Coupled circuits means basically electromagnetic induction. When you give electricity through a coil, magnetism is developed. So that's what we are going to see now. That's called coupled circuits, which has a link to mutual inductance. First, let us see some fundamental definitions. Then we'll go to some rules for polarity. With that, we will be drawing the equivalent circuit. Once the equivalent circuit is drawn, we can do anything. That's why most of the examiners are interested in equivalent circuits. Because if you know equivalent circuit, you know equations. If you know equations, you know the solution. This is all about AC analysis. Let's start. First definition is self-inductance. Self-inductance we call L for inductance. Generally, whenever the current flows through a conductor, a magnetic field is created around the conductor. This is due to inductance. Suppose even if you take a conductor, if you send some current through that, definitely flux will be there. Why? According to electromagnetic theory, the very important concept in magnetic field is produced due to current. So when current flows, magnetic field is developed. With that idea, this concept of coupled circuits came, magnetic field came, and mutual EMF came. The second idea is mutual inductance. Magnetic field is created in another coil, then it is called mutual inductance. Please understand, if the EMF is generated within the same coil, it is called self-EMF. If the EMF is generated in another coil due to the current in another coil, that is called mutual EMF. And this is physically, there is no physical element here, but still there is an effect. Like we see inductor, we don't see M. M is not physically existing. It is basically existing as just an effect. For that's why I given a statement here. These two coils we see here, they are isolated. There is no connection between them. That's why I have written a sentence: electrically isolated and magnetically coupled. These two coils, they are coupled with magnetism or magnetic flux, but they have no link between them. That's why observe here is a electricity, voltage you are giving, that voltage is developing magnetic field. This magnetic field in link with that produce there, and the current can flow. This is what exactly the transformer operation. That's why we have to think of this coupling concept also. Then when two inductors are coupled together, we have to define the third one called coupling coefficient. The degree of closeness between the two coils is nothing but coupling coefficient. So the coupling coefficient is called degree of closeness. How close they are, and if they are very close, you can have more effect also. That's why mutual inductance is defined as K into root of L1, L2. L1, L2 are self-inductances. When two self-inductances are brought together, you have mutual inductance. So mutual inductance is K into root of L1, L2. K is generally 0 to 1. There, if we take it, but practically, if it is less than 1, we call it as lightly coupled. If it is equal to 1, we call critically coupled. If it is greater than 1, we call tightly coupled. If K is 0 to 1, M is less than or equal to root of L1, L2. If K is 1 here. So M cannot be more than L1 or L2. Right? This is called coupling coefficient. Then polarity rule. According to dot rule, when currents are entering the dot, then it is taken as positive polarity. And if the current is leaving the dot, it can be taken as negative polarity. I am giving you example here. Look at here. Current is entering the dot. So we should take positive. So what is the voltage across this inductor? L di by dt. That everybody knows. Right from the beginning of my lectures I have been telling. But today's idea is not that. Today's idea is how much coupling is there, what is the polarity of coupling. So here V is equal to L di by dt. This is with positive sign. Here you see current is entering, but the dot is at the leaving. This is opposite sign. That's why V is equal to minus L di by dt. So this is an idea to tell you how to put the polarities. If polarity is known, you will put the dot. If dot is known, you will put the polarity. Very simple. So this is about how to write an equation and how to consider the polarities. Then I have given one interesting statement. Polarity of induced EMF is same as self EMF if both currents are entering the coil or leaving the coil. Suppose if both currents are entering the coil or leaving the coil, suppose if they enter the dot and enter. So if both currents are entering the dots while entering the coil, if both currents are leaving the dots while entering the dots while leaving, in both cases we put the same EMF. If it is opposite, if it is otherwise, we put opposite polarity. Please follow. I will just demonstrate this statement here. Look at here. Same current. Here it is entering the dot and entering the coil. Here also entering the dot, entering the coil. That means similar polarity. We should take same as self EMF. Then first let me draw the equivalent. What is equivalent? Look at here. This is positive, negative. Why? For example, first of all, put this value m di by dt, m di by dt. What is the polarity of induced EMF? Polarity of induced EMF is same as self EMF. Polarity of induced EMF is same as self EMF. How is it? Positive, negative. This is also positive, negative. First, why it is same? Because they both are entering the dot. If both are entering the dot and entering the coil, it should have same polarity. So please understand, this is the current direction, therefore plus minus. This plus minus is for self EMF, and self EMF polarity and induced EMF polarity both are same. Similarly, here plus minus, this also plus minus. So polarity of self EMF and induced EMF is both are same. This is what I mean by the word, how you understand it. So this is the equivalent circuit for this circuit along with polarities. But remember, why do I put this dependent source level? Because this is not existing. It is depending on current. So when it is depending on current, we should really say, which is not physically existing, better put it as dependent source. As I told in the definition, induced EMF is not seen physically. So it has become a custom, or it's become an approach to always put induced EMF as dependent source. That too, this is voltage sources. Current develops voltage. That is the meaning of induced EMF. So my next example would be opposite polarity. Look at that. So if you want to see both are entering, that is idea. If both are opposite, you can see. So that you can see in my problems. Let me go into problems directly. I will be incorporating some ideas along with the problems, because We can't see theory and problem separately. That will take a lot of time. Unnecessary waste of time. Problem 1. Obtain equivalent inductance for the circuit shown in figure. Look at the problem. Please understand, if dots are there, then only there is an indication of induced EMF. Or if M is mentioned, there is an indication of EMF. Why I am saying is, in all my previous lectures, I took inductance, but nowhere I considered induced EMF. So now I am considering. That's why you have two ideas here. Dots must be there or M must be there to say that there is a coupling. Look at here. This is a dot entering. This also entering. That means what? Both are similar. Okay? Both are similar. Now the best thing, why similar? Both are entering. Therefore, induced EMF is same as self EMF. Now let me give you the solution. In solution, the first thing is equivalent circuit. Look at the equivalent circuit here. For example, L1 as it is, L2 as it is. M di by dt, M di by dt. What will happen? Plus minus. Why plus minus? Current is going in this direction. When current is going in this direction, we say plus and minus. Therefore, this is same as this. This also plus minus same as this. So, the self EMF will decide the mutual EMF. So, mutual EMF, self EMF both are same, plus minus, plus minus, plus minus, plus minus, right? This is an idea. So, if I apply KVL, input voltage is equal to L di by dt, okay, M di by dt plus L2 di by dt plus M di by dt. Now, if you take di by dt common, what is happening? L1 plus L2 plus 2M. This is actually called L equivalent. So, in the place of M, in the place of inductance, you have L1 plus L2 plus 2M. Because this is added, suppose if it is subtracted, you will have minus 2M. So, for examiner, most of the times he is interested in plus or minus. This is the equivalent. He is simply asking for equivalent inductance. That's the equivalent and that is the solution. Let me give you second problem. Obtain equivalent inductance for the circuit shown in figure. What do you say? There is a dot here entering, whereas here leaving. So, one is entering, other is leaving, or current is entering while entering the dot, current is entering the dot while leaving. So, one is while entering, other is while leaving. If these things are opposite, we should say opposite polarity. Therefore, you just wait and see how I am going to draw the equivalent. Same as previous. It has inductance, it has M. Inductance, M. Then what is the difference? Because I said opposite, you see, plus minus here, therefore minus plus. Plus minus, minus plus. This is the equivalent circuit. Now, if I apply the KVL, L1 plus L2 minus M minus M. So, it becomes minus 2M. Therefore, L equivalent is L1 plus L2 minus 2M. Please understand how it came. Like this, you can also handle the parallel circuits. Whether it is a series circuit or parallel circuit, the main idea is how to calculate the equivalent inductance when there is coupling. When there is a coupling, how to handle this, right? That's about second problem. Let's go to third problem. Before going to third problem, as I said, parallel equivalents, how to handle. See, L1, L2, both are same dots. L1, L2 minus M square by L1 plus M2 minus 2M. Opposite dots, L1, L2 minus M square by L1 plus L2 plus 2M. As I has been telling, you have minus sign, you have plus sign. So, this is also can be derived, but This derivation is left to the student to do it, but this is the conclusion. So we have seen equivalent for serial with both dots, and we have taken parallel both dots, opposite and same. So this is all introductory ideas to enter into further problems. Let's go to third problem. With this approach and introduction I gave, I'm entering into examination problems. Calculate L equivalent for the circuit shown. Calculate L equivalent for the circuit shown. Say this is L1, this is L2. When this is L1 and L2, what is the effective equivalent here? That is L1, L2. One is entering, other is leaving. So without further wasting of time, we can simply say L1 plus L2 minus 2m, because it is just like our second problem. But anyway, follow me as I go through the solution. The equivalent circuit is given as follows. Apply KVL in the loop. More serious matter is equivalent circuit. This is opposite. Plus minus means opposite. Plus minus opposite. If you put them into loop, you will say L1 plus L2 minus 2m. L1 plus L2 minus 2m. That's called L equivalent, right? So this is all about an equivalent asked in the exam. Therefore, answer option is A. Let's go to fourth problem. Now I am still further complicating or increasing. The question is same. Calculate L equivalent for the circuit. Look at here. Say this is L1, L2, L3. From L1 to L2 you have 2H. We call it as M12. This is M23. This is M13. We need to calculate the dots here. Good. Now look at this. First add all the three. Okay. Then the question comes how to handle this. From here, entering. So it should have one is entering, while this is while leaving, this is while entering. So for this 2H, it is opposite polarity. That's why minus is there. This is while entering, this is while entering. Both are entering, therefore it should have same polarity. Okay. Next, this is while leaving, this is while entering, opposite. That means first one is opposite, last one is opposite, only this one is same. That means minus 2, minus of minus become plus, minus of minus plus become minus. That means 12 minus 2 into 2 minus 1 plus 1. If you cancel 1 and 1, you will have 2. That is 4. 12 minus 4 is 8. So this is how equivalent has to be taken. So option is D. 8 is your option C here. So this is given for 2 marks. Is a very surprising, because the difficulty involved in coupled circuits, they wanted to give 2 marks. Okay. Enjoy and better score it well with this. Problem 5. Calculate L equivalent for the circuit shown in figure. This also given for 2 marks because too many. Whenever there is a single coupling, they are giving 1 mark. If you have more couplings, they are giving 2 marks. So look at here. Simply 4 plus 5 plus 6. Okay. Then question comes whether it is minus or here. Look at here. This is M entering. This one leaving. So it should be minus 1. It's not simply 1. Why should we take minus 2 into 1? Because this couples there, this couples here. So 2. This is coupling on this coil, this coupling on this coil, therefore 2. So minus 2 here. Then this is while leaving, this is while leaving, positive. That means 2 into 2, 4. Then this is while entering, this is while leaving, opposite. Like this, if both coils, you should understand whether it is opposite means minus sign, same means positive sign, right? Come with me. Look at here, L1 plus L2 plus L3 as it is, 2 into minus, because this is entering, leaving, so opposite. Second, I will give you explanation for each one. Plus 2, why plus 2? This is while leaving, this is also while leaving. So this is basically same. Same means plus. Then why minus 3? Because this 3 entering here, leaving here. One is entering, other is leaving, therefore it has to be minus 3. Then each one is coupling 2 times, that's why we anyway put 2 here. So 2 into minus 1, minus 3, minus 4, so minus 2, minus 4, so 11. Okay, so you have to 11, and this 4 and minus 4 will cancel. Answer is 11. So seriously observe the polarity. Altogether it matters with polarity. If dots are in the same, positive. If dots are opposite, so positive sign for same dots, negative sign for opposite dots. Therefore option is C. So this is how different options have come into this coupled circuits. Let me take you for sixth problem. Sixth problem is calculate L equivalent for the circuit. As I told you, parallel. This is mutual coupling is 8, 15 and 16. This is the problem given. We have taken into in order to explain how to consider parallel circuits. Come here. As I given in the explanation, L1 into L2 minus L1 L2 there. See, m square. So L1 L2 m square means 8 square 64 by L1 plus L2 plus 2 into m. Why plus 2? Because these two are opposite. Okay. Actually speaking, if you take this current, you will understand why minus. Because this is while leaving, this is while leaving, you see. Therefore, for the same, you have to put positive. So look at the approach I am telling you. Suppose you take a current here. This is entering the dot while leaving. This is also entering the dot while leaving. So both are leaving means what? Same polarity. Same means plus. So this is what? Plus. Otherwise, that is one explanation I gave you. Another explanation can be L1 15 minus 8, L2 16 minus 8, and L1 L2 by 1 by L1, 1 by L2, or L1 L2 by L1 plus L2 will give you 3 points. So the best would be the standard equation you can always substitute. This is to tell you about parallel circuit. Option is A. Look at this option 7 4. Okay. Question number 7. Obtain mesh equation for the circuit shown in figure. Here is a circuit. You have a resistor, inductor and capacitor. M shows there is a mutual inductance, dot and dot here. For I1 this is entering, for I2 this is entering. So both are entering, that means both are same. Same means same polarity. Now let's see the equivalent circuit. The two coils are having similar polarity, therefore we are going to have plus minus plus minus, plus minus plus minus, same. V is IR1 j omega L1 j omega m I2. Please remember, second one will induce on the first one and first one will induce on the second one. Therefore, j omega L2 I2 1 by j omega c I2 and j omega m I1. So because when I say I1 is induced along with I2. I2 is induced along with I1. These are the two different options. Good. So always coupling is not in the same coil but in the opposite coil. These are the two equations for this equivalent given. So we have to draw the equivalent and then make the equation, right? This is how we can write the equations also. Once you write the equations, solving is very simple. Solution is very simple. That's why most of the examiners will ask only equations. Right. Let's go to 8th problem. Obtain mesh equation for the circuit shown. For this circuit, we have to go for mesh equation. This is entering, this is I1, this is I2. So what is happening here? You can see one is entering, other is also, this is entering, but this is while leaving. So you should have opposite. That opposite I am going to show here. First come to the circuit. This is plus minus. That opposite means what? Minus plus. This is plus minus, minus plus. Understand? Now what is this induced EMF? Second one is inducing on first one. This here, first one is inducing on second one. That's why when I write here M di1 by dt, when I write here M di2 by dt. Therefore, Vn is equal to L di1 by dt minus M di plus L3 into I1 minus I2. Similarly, if you go here, L2, then go for this, and this is just like once you draw the equivalent circuit, writing the equation is after all very simple job. But they are maximum they are asking you to go for equivalent circuit and equation, no solution. In objective question papers they cannot ask you solution, right? This is about another problem. So let's go to next problem 9. I am complicating the problem. Obtain equivalent circuit for the circuit shown in figure. Why do I complicate here? First one 1 2 3 2 3 1 2. So this is between first coil to third coil. This is between first coil to second coil. This is between second coil to third coil. So there are 3 inductances available. When you have 3 inductances and all the 3 are linked together, then you will have lots of big complicated circuit. That's why he is not asking equations, he is simply asking only circuit. First draw the equivalent circuit. Actually speaking, you can also treat this as linked problems. You know, when you say linked problem, the linked problem means the answer of the first one will act as a data for the second one. When the answer is acting as data, we normally call it a linked problem. So you can take every problem in coupled circuits as linked problems. What is the link in that problems actually? Look at that. Equivalent circuit is always one part, and then you can go for the equation. So you can never try for equation without equivalent circuit. Therefore, look at this circuit diagram. Good. Now tell me one thing straight away. This is entering, this is leaving. So M12 is opposite. This is entering, this is entering. But this is entering with respect to I1, this is leaving with respect to I2. Therefore, this is going to be opposite. And here I2 respect, this is leaving. I1 respect, this is entering. So you have again opposites there. So let me show you the equivalent circuit. So seems to be difficult, but try to understand. This is self EMF. This is EMF due to L3. Please remember, for this I2 minus I1 is here. So for this EMF, it's not one current doing, it is two currents doing. And this one is only due to second. That is, first you must write EMF, polarity we will see later. First, mutual EMF due to what currents? I2 minus I1. And this mutual EMF due to what current? I2. So, on each coil we have two induced EMFs. That's very interesting. That's why this is the maximum complicated problem in coupling circuits, or in fact the total network theory. Now, when I come to here, what will be inducing? This will be induced due to I1. This will be induced due to I1 in opposition with I2. So, got it? So, in L2 you have two inductions, in L1 you have two inductions. In L3 also you have two inductions. L1 due to I1 inducing here, L2 due to I1 is inducing here. So, there are two inductions possible here. Okay. But very interestingly, in this induction, when this is inducing here, only I1. When this is inducing here, only I2. That's why you don't have two currents. Due to this you have two currents, but otherwise only one current. This is the equivalent circuit you have. So, when you have the equivalent circuit in this way, I1 and I2, okay. Once the equivalent is ready, equation is always very simple thought. But now I am having a challenge of explaining you the polarities. So, there is always three important things. First is there a induction? If there is induction, due to what current? And after that, what polarity? If these two are done, you are right. Now look at here, M13 same as this. M12 is opposite. So here it is same, here it is opposite. So same as means plus minus means I have put plus minus, and opposite means minus plus. So you have to decide whether it is same or opposite. Similarly, I am taking you here. What is same? M12 is opposite. We already decided. If this is opposite here, here also it will be opposite. Please remember another serious matter that I forgot to tell you so far. M12 is equal to M21. The coupling from first coil to the second coil is same as coupling from the second coil to the first coil. So these are the couplings that we have. Okay. So when we have this coupling, whatever the value here, the same value comes there, but only difference is this is due to I1, whereas this is due to I2. Because on the first coil, second one has to induce. On the second coil, first one has to induce. So I1 induce here, but the polarity is with respect to I2. So see there, plus minus, we already said minus plus. So M12 is opposite, therefore here also opposite, plus minus minus plus. Next one, M23. How is M23? That is also opposite of this plus minus, so minus plus. Good idea. So this is how we can put the polarities also. Now having got the polarities, are you ready? Now let me talk about these polarities. Very simple. Simply look at this. This is inducing from where? I1. This is inducing from I1. So I1 inducing means M13. M13 here. What is the polarity? First find the polarity of I2, minus plus, so same as. Please observe here, here it is same, here also same. The only same means what? This polarity is with respect to this polarity is with respect to this. And finally 2, 3. What about 2, 3? Opposite. So this is plus minus means opposite, minus plus. So this is loop current I1, this is loop current I2, this is the total equivalent circuit we have. Because it is complicated equivalent circuit, it is given as 2 marks directly. Only objective question without any equations. In fact, drawing the circuit is more difficult than equations. But remember, if equivalent circuit is wrong, equations are automatically wrong. Then let me take you to equations. That's my next problem. Question number 10. Obtain the mesh equations for the equivalent circuit of the above problem. So first, this equivalent circuit was developed in the previous question called 9th question. So I have just borrowed it from there to here for you to understand this. Now once the equivalent is ready, I am simply applying KVL, KCL. Look at here. Vn is equal to L1 di by dt. Di by dt is nothing but j omega L1. M13. This is j omega M13. Next, M12. M12 with the j omega. So very simply to say, wherever there is a differentiation, it is j omega. Similarly, look at here. This only was done, and this also should be completed. J omega L3, what is the current flowing in this? I1 minus I2. Then j omega M13 I1, j omega M23 I2. So this is the completeness of this equation. Okay, this is the equation we have. Next, look at for the second Kirchhoff's laws. When I apply KVL for the second loop, what happens? J omega L2, j omega M12 I1, j omega M23 I1 minus I2. Just follow this. Okay. Then looking here, M23 I2, M13 I1, then j omega L3 I2. The polarities as already there in the circuit. So this is second equation that you have. So once the equation is ready, solution is anyway done. That's why once again I am telling there are 3 ways of writing the equation. Time domain, L di by dt. Frequency domain, j omega L. S domain, Ls into I. So you can have the equation, any form of the 3 things and solve it. But as I've been telling in every different parts of the lecture, I am once again concluding to tell you that whether you do in any transform, the solution is simple. Suppose if you do in frequency domain, solve, but answer will come in frequency domain. After taking inverse transform, you will get I of t. If you do the whole process in S domain, you will get I of s, then inverse transform I of t. Like that, because solving in time domain is definitely a laborious job. So when you solve in the equation, it's becoming a laborious. So therefore people normally prefer, instead of time domain, they go to frequency domain using Fourier transform, or they go to S domain using Laplace transform. So frequency domain and S domain, they just came for Fourier transform and Laplace transform. They just came to help you to convert the integrals and differentials or integral differential equation into linear algebraic, and the solution becomes very simple. Because solving algebra is very easy compared to integral differentials. This is how we have using this frequency domain techniques here, right? So these are the different options available in coupled circuits. With that, almost we have finished our AC circuits. As I said, there is only one small topic, that is none other than filters. That we'll be seeing in the next class. With that, I am going to close AC part and then take you for the last topic called 2 ports there. So these are the different parts of